is fired first, to trigger the active defenses, with the real warhead following it. For example, the RPG-29 from the 1980s is able to penetrate the frontal hull armor of the Challenger 2 and also managed to damage AM-1 Abrams. As well, even tanks with advanced armor plating can have their tracks or gearcox damaged by RPGs, which may render them immobile or hinder their mobility. Despite all of the advances in armor plating, a tank with its hatches open remains vulnerable to Molotov cocktail, gasoline bombs, and grenades. Even a buttoned-up tank may have components which are vulnerable to Molotov cocktails, such as optics, extra gas cans and extra ammunition stored on the outside of the tank. Avoiding detection. Further information, military deception. PLA's Type 99, a tank with disruptive camouflage painting. A tank avoids detection using the doctrine of countermeasures known as CCD. Camouflage, looks the same as the surroundings. Concealment, cannot be seen, and deception, looks like something else. Camouflage. Further information, military camouflage. Camouflage can include disruptive painted shapes on the tank to break up the distinctive appearance and silhouette of a tank. Netting or actual branches from the surrounding landscape are also used. Prior to development of infrared technology, tanks were often given a coating of camouflage paint that, depending on environmental region or season, would allow it to blend in with the rest of its environment. A tank operating in wooded areas would typically get a green and brown paint job. A tank in a winter environment would get white paint, often mixed with some darker colors. Tanks in the desert often get khaki paint jobs. The Russian Nakedka camouflage kit was designed to reduce the optical, thermal, infrared, and radar signatures of a tank, so that acquisition of the tank would be difficult. According to Nihai Stali, the designers of Nakedka would reduce the probabilities of detection via visual and near-IR bands by 30%, the thermal band by 2-3-fold, radar band by 6-fold, and radar thermal band to near background levels. Concealment. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. November 2018. Learn how and when to remove this message. Concealment can include hiding the tank among trees or digging in the tank by having a combat bulldozer dig out part of a hill, so that much of the tank will be hidden. A tank commander can conceal the tank by using hull-down approaches to going over upward sloping hills, so that she or he can look out the commander's cupola without the distinctive-looking main cannon cresting over the hill. Adopting a turret-down or hull-down position reduces the visible silhouette of a tank as well as providing the added protection of a position in defilade. Working against efforts to avoid detection is the fact that a tank is a large metallic object with a distinctive, angular silhouette that emits copious heat and engine noise. A tank that is operating in cold weather or which needs to use its radio or other communications or target detecting electronics will need to start its engine regularly to maintain its battery power, which will create engine noise. Consequently, it is difficult to effectively camouflage a tank in the absence of some form of cover or concealment, for example, woods. It can hide its hull behind. The tank becomes easier to detect when moving, typically, whenever it is in use, due to the large, distinctive auditory, vibration and thermal signature of its engine and power plant. Tank tracks and dust clouds also betray past or present tank movement. Switched-off tanks are vulnerable to infrared detection due to differences between the thermal conductivity and therefore heat dissipation of the metallic tank and its surroundings. At close range the tank can be detected even when powered down and fully concealed due to the column of warmer air above the tank and the smell of diesel or gasoline. Thermal blankets slow the rate of heat emission, and some thermal camouflage nets use a mix of materials with differing thermal properties to operate in the infrared as well as the visible spectrum. Grenade launchers can rapidly deploy a smoke screen that is opaque to infrared light, to hide it from the thermal viewer of another tank. In addition to using its own grenade launchers, a tank commander could call in an artillery unit to provide smoke cover. Some tanks can produce a smoke screen. Sometimes camouflage and concealment are used at the same time. For example, a camouflage-painted and branch-covered tank, camouflage, may be hidden behind a hill or in a dug-in emplacement, concealment. Deception. Some armored recovery vehicles, often tracked, tank chassis-based tow trucks for tanks, have dummy turrets and cannons. This makes it less likely that enemy tanks will fire on these vehicles. Some armies have fake dummy tanks made of wood which troops can carry into position and hide behind obstacles. These dummy tanks may cause the enemy to think that there are more tanks than are actually possessed. Armor. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. January 2013. Learn how and when to remove this message. Main article, Vehicle Armor. To effectively protect the tank and its crew, tank armor must counter a wide variety of anti-tank threats. Protection against kinetic energy penetrators and high-explosive anti-tank, heat, shells fired by other tanks is of primary importance, but tank armor also aims to protect against infantry mortars, grenades, rocket-propelled grenades, anti-tank guided missiles, anti-tank mines, anti-tank rifles, bombs, direct artillery hits, and, less often, nuclear, biological and chemical threats, any of which could disable or destroy a tank or its crew. Steel armor plate was the earliest type of armor. The Germans pioneered the use of face-hardened steel during World War II, and the Soviets also achieved improved protection with sloped armor technology. World War II developments led to the obsolescence of homogeneous steel armor with the development of shaped charge warheads, exemplified by the Panzerfaust and bazooka infantry carried weapons which were effective, despite some early success with spaced armor. Magnetic mines led to the development of anti-magnetic paste and paint. From World War II to the modern era, troops have added improvised armor to tanks while in combat settings, such as sandbags or pieces of old armor plating. British tank researchers took the next step with the development of Kavorm armor, or more generally composite armor, incorporating ceramics and plastics in a resin matrix between steel plates, which provided good protection against heat weapons. High-explosive squash-head warheads led to anti-spall armor linings, and kinetic energy penetrators led to the inclusion of exotic materials like a matrix of depleted uranium into a composite armor configuration. Reactive armor consists of small explosive-filled metal boxes that detonate when hit by the metallic jet projected by an exploding heat warhead, causing their metal plates to disrupt it. Tandem warheads defeat reactive armor by causing the armor to detonate prematurely. Modern reactive armor protects itself from tandem warheads by having a thicker front metal plate to prevent the precursor charge from detonating the explosive in the reactive armor. Reactive armors can also reduce the penetrative abilities of kinetic energy penetrators by deforming the penetrator with the metal plates on the reactive armor, thereby reducing its effectiveness against the main armor of the tank. Active protection system. The latest generation of protective measures for tanks are active protection systems. The term active is used to contrast these approaches with the armor used as the primary protective approach in earlier tanks. 1. Soft kill measures, such as the Russian Shtera countermeasure system, provide protection by interfering with enemy targeting and fire control systems, thus making it harder for the enemy threats to lock onto the targeted tank. 2 hard kill systems intercept incoming threats with a projectile of its own, destroying the threat. For example, the Israeli Trophy destroys an incoming rocket or missile with shotgun-like projectiles. The Soviet Drozd, the Russian Arena, the Israeli Trophy and Iron Fist, Polish Irawa, and the American Quick Kill systems show the potential to dramatically improve protection for tanks against missiles, RPGs and potentially kinetic energy penetrator attacks, but concerns regarding a danger zone for nearby troops remain. Mobility. The mobility of a tank is described by its battlefield or tactical mobility, its operational mobility, and its strategic mobility. One tactical mobility is the tank's ability to move through the battle area. This could include acceleration, braking, speed and rate of turn on varying terrain, and obstacle clearance, the tank's ability to travel over or through obstacles like walls, trenches, and water. 2 operational mobility is the ability to move tanks hundreds of kilometers from a staging area to the battle area, for example, by using transport helicopters. 3 strategic mobility is the ability of the tanks to be transported over long distances, usually by air or sea. For tanks to be transported efficiently by air, weight and volume must be kept within the transport aircraft's capabilities. Suspension and running gear. Tank agility is a function of the weight of the tank due to its inertia while maneuvering and its ground pressure, the power output of the installed power plant and the tank transmission and track design. In addition, rough terrain effectively limits the tank's speed through the stress it puts on the suspension and the crew. A breakthrough in this area was achieved during World War II when improved suspension systems were developed that allowed better cross-country performance and limited firing on the move. Systems like the earlier Christie or later torsion bar suspension developed by Ferdinand Porsche dramatically improved the tank's cross-country performance and overall mobility. Tracks. Tanks are highly mobile and able to travel over most types of terrain due to their continuous tracks and advanced suspension. The tracks disperse the weight of the vehicle over a large area, resulting in less ground pressure. A tank can travel at approximately 40 km per hour, 25 miles per hour, across flat terrain and up to 70 km per hour, 43 miles per hour, on roads. But due to the mechanical strain this places on the vehicle and the logistical strain on fuel delivery and tank maintenance, these must be considered burst speeds that invite mechanical failure of engine and transmission systems. Consequently, wheeled tank transporters and rail infrastructure is used wherever possible for long-distance tank transport. The limitations of long-range tank mobility can be viewed in sharp contrast to that of wheeled armored fighting vehicles. The majority of blitzkrieg operations were conducted at the pedestrian pace of 5 km per hour, 3.1 miles per hour, and that was only achieved on the roads of France. Engine. The tank's power plant supplies kinetic energy to move the tank, and electric power via a generator to components such as the turret rotation motors and the tank's electronic systems. The tank power plant evolved from predominantly petrol and adapted large displacement aeronautical or automotive engines to diesel engines. Japan was the first to begin transitioning to this engine type beginning with the Type 89B in 1934. The main advantage of diesel is their higher fuel economy, which allows for greater operating ranges. Diesel engines can also run on a variety of fuels, such as aviation kerosene and even gasoline. Advanced multi-fuel diesel engines have been adopted. Powerful, per unit weight, but fuel-hungry gas turbines have seen some limited use, namely by the Soviet T-80 and American M1 Abrams. The transition from petrol to diesel. Tank power output and torque in context. Vehicle power output, power forward/weight torque. Mid-sized car Toyota Camry 2.4 L 118 kilowatts, 158 HP, 79 kilowatt forward/T, 106 HP forward/T, 218 Nm, 161 lb-ft. Sports car Lamborghini Murcielago 6.5 L 471 kilowatts, 632 HP, 286 kilowatt forward/T, 383 HP forward/T, 660 Nm, 490 lb-ft. Racing car Formula 1 car 3.0 L 710 kilowatts, 950 HP, 1065 kilowatt forward/T, 1428 HP forward/T, 350 Nm, 260 lb-ft. Main battle tank Leopard 2, M1 Abrams 1100 kilowatts, 1500 HP, 18.0 to 18.3 kilowatt forward/T, 24.2 to 24.5 HP forward/T, 4700 Nm, 3500 lb-ft. Locomotive SNCF Class T 2000 1925 kilowatts, 2581 HP, 8.6 kilowatt forward/T, 11.5 HP forward/T. Fording. In the absence of combat engineers, most tanks are limited to fording small rivers. The typical fording depth for MBTs is approximately 1 m, 3.3 feet, being limited by the height of the engine air intake and driver's position. Modern tanks such as the Russian T-90 and the German Leopard 1 and Leopard 2 tanks can ford to a depth of 3 to 4 m, 9.8 to 13.1 feet, when properly prepared and equipped with a snorkel to supply air for the crew and engine. Tank crews usually have a negative reaction towards deep fording, but it adds considerable scope for surprise and tactical flexibility in water crossing operations by opening new and unexpected avenues of attack. Amphibious tanks are specially designed or adapted for water operations, such as by including snorkels and skirts, but they are rare in modern armies, being replaced by purpose-built amphibious assault vehicles or armored personnel carriers in amphibious assaults. Advances such as the EFA mobile bridge and armored vehicle-launched scissors bridges have also reduced the impediment to tank advance that rivers posed in World War II. Crew. Tank commander redirects here. For other uses, see Tank commander, disambiguation. Most modern tanks most often have 4 crew members, or 3 if an autoloader is installed. These are the 1 commander. The commander is responsible for commanding the tank, with all-round vision devices rather than the limited ones of the driver and gunner. He guides the gunner roughly onto target and guides the driver around turns and obstacles. 2 gunner. The gunner is responsible for laying the gun, the process of aiming an artillery piece at targets. It may be laying for direct fire, where the gun is aimed similarly to a rifle, or indirect fire, where firing data is calculated and applied to the sights. The term includes automated aiming using, for example, radar-derived target data and computer-controlled guns. Gun laying means moving the axis of the bore of the barrel in 2 planes, horizontal and vertical. A gun is traversed, rotated in a horizontal plane, to align it with the target, and elevated, moved in the vertical plane, to range it to the target. 3 loader. The loader loads the gun, with a round appropriate to the target, heat, smoke, etc., as ordered by either the commander or the gunner. The loader is usually the lowest ranked member of the crew. In tanks with autoloaders this position is omitted. For driver, the driver drives the tank, and also performs routine maintenance on the automotive features. Operating a tank is a team effort. For example, the loader is assisted by the rest of the crew in stowing ammunition. The driver is assisted in maintaining the automotive features. Historically, crews have varied from just 2 members to a dozen. First World War tanks were developed with immature technologies. In addition to the crew needed to man the multiple guns and machine guns, up to 4 crewmen were needed to drive the tank. The driver, acting as the vehicle commander and manning the brakes, drove via orders to his gearsmen. A co-driver operated the gearbox and throttle, and 2 gearsmen, one on each track, steered by setting one side or the other to idle, allowing the track on the other side to slew the tank to one side. Pre-World War II French tanks were noted for having a 2-man crew, in which the overworked commander had to load and fire the gun in addition to commanding the tank. With World War II the multi-turreted tanks proved impracticable, and as the single turret on a low-hull design became standard, crews became standardized around a crew of 4 or 5. In those tanks with a 5th crew member, usually 3 were located in the turret, as described above, while the 5th was most often seated in the hull next to the driver, and operated the hull machine gun in addition to acting as a co-driver or radio operator. Well-designed crew stations, giving proper considerations to comfort and ergonomics, are an important factor in the combat effectiveness of a tank, as it limits fatigue and speeds up individual actions. Engineering constraints. A noted author on the subject of tank design engineering, Richard Agorkiewicz, outlined the following basic engineering subsystems that are commonly incorporated into tanks' technological development. 1. Mobility of tanks, through chassis design. 2. Tank engines. 3. Tank transmissions. 4. Suspensions and running gear. 5. Soil vehicle mechanics. 6. Tank guns and ammunition. 7. Ballistics and mechanics of tank guns. 8. Vision and sighting systems. 9. Illuminating and night vision systems. 10. Fire control systems for main and auxiliary weapons. 11. Gun control systems. 12. Guided weapons. 13. Armor protection. 14. Configuration of tanks. To the above can be added unit communication systems and electronic anti-tank countermeasures, crew ergonomic and survival systems, including flame suppression, and provision for technological upgrading. Few tank designs have survived their entire service lives without some upgrading or modernization, particularly during wartime, including some that have changed almost beyond recognition, such as the latest Israeli Magak versions. The characteristics of a tank are determined by the performance criteria required for the tank. The obstacles that must be traversed affect the vehicle's front and rear profiles. The terrain that is expected to be traversed determines the track ground pressure that may be allowed to be exerted for that particular terrain. Tank design is a compromise between its technological and budgetary constraints and its tactical capability requirements. It is not possible to maximize firepower, protection and mobility simultaneously while incorporating the latest technology and retain affordability for sufficient procurement quantity to enter production. For example, in the case of tactical capability requirements, increasing protection by adding armor will result in an increase in weight and therefore decrease in mobility. Increasing firepower by installing a larger gun will force the designer team to increase armor, the therefore weight of the tank by retaining same internal volume to ensure crew efficiency during combat. In the case of the Abrams MBT, which has good firepower, speed and armor, these advantages are counterbalanced by its engine's notably high fuel consumption, which ultimately reduces its range, and in a larger sense its mobility. Since the Second World War, the economics of tank production governed by the complexity of manufacture and cost, and the impact of a given tank design on logistics and field maintenance capabilities, have also been accepted as important in determining how many tanks a nation can afford to field in its force structure. Some tank designs that were fielded in significant numbers, such as Tiger I and M60A2, proved to be too complex or expensive to manufacture, and made unsustainable demands on the logistics services support of the armed forces. The affordability of the design therefore takes precedence over the combat capability requirements. Nowhere was this principle illustrated better than during the Second World War, when two Allied designs, the T-34 and the M4 Sherman, although both simple designs which accepted engineering compromises, were used successfully against more sophisticated designs by Germany that were more complex and expensive to produce, and more demanding on overstretched logistics of the Wehrmacht. Given that a tank crew will spend most of its time occupied with maintenance of the vehicle, engineering simplicity has become the primary constraint on tank design since the Second World War, despite advances in mechanical, electrical and electronics technologies. Since the Second World War, tank development has incorporated experimenting with significant mechanical changes to the tank design while focusing on technological advances in the tank's many subsystems to improve its performance. However, a number of novel designs have appeared throughout this period with mixed success, including the Soviet IT-1 and T-64 in firepower, and the Israeli Merkava and Swedish S-tank in protection, while for decades the US M551 remained the only light tank deployable by parachute. Further information: tank classification, command, control, and communications. Commanding and coordinating tanks in the field has always been subject to particular problems, particularly in the area of communications. But in modern armies these problems have been partially alleviated by networked, integrated systems that enable communications and contribute to enhanced situational awareness. 20th century. World War I and interwar period. Armored bulkheads, engine noise, intervening terrain, dust and smoke, and the need to operate with hatches closed are severe detriments to communication and lead to a sense of isolation for small tank units, individual vehicles, and tank crew. Radios were not portable or robust enough to be mounted in a tank, although Morse code transmitters were installed in some Mark IVs at Cambridge's messaging vehicles. The mounting of a field telephone to the rear was not a practice. During World War I, when these failed or were unavailable, situation reports were sent back to headquarters by some crews releasing carrier pigeons through loopholes or hatches, and communications between vehicles was accomplished using hand signals, handheld semaphore flags which continued in use in the Red Army/Soviet Army through the Second and Cold Wars, or by foot or horse-mounted messengers. World War II. From the beginning, the German military stressed wireless communications, equipping their combat vehicles with radios, and drilled all units to rely on disciplined radio use as a basic element of tactics. This allowed them to respond to developing threats and opportunities during battles, giving the Germans a notable tactical advantage early in the war. Even where Allied tanks initially had better firepower and armor, they generally lacked individual radios. By mid-war, Western Allied tanks adopted full use of radios, although Russian use of radios remained relatively limited. Cold War era. On the modern battlefield, an intercom mounted in the crew helmet provides internal communications and a link to the radio network, and on some tanks an external intercom on the rear of the tank provides communication with cooperating infantry. Radio networks employ radio voice procedure to minimize confusion and chatter. A recent development in AFV equipment and doctrine is integration of information from the fire control system, laser rangefinder, global positioning system and terrain information via hardened military specification electronics and a battlefield network to display information on enemy targets and friendly units on a monitor in the tank. The sensor data can be sourced from nearby tanks, planes, UAVs or, in the future, infantry, such as the U.S. Future Force Warrior project.